Today we are going over lesson 16, and so far this semester we've talked about the different ways we can integrate. One is by taking the antiderivative or undoing the power rule for derivatives. The second method was use substitution. And then the last method we talked about was using various formulas, trig identities, algebraic manipulation like completing the square. Now, what if you cannot do any of those methods? Well, that leads us to today's method called integration by parts. And here's the specific formula. Basically, if you have a product of two kind of unrelated functions, then you use integration by parts. So here's the formula. The integral of u dv, which is your original problem, is equal to u times v minus the integral of v du, in which the u represents your normal u substitution, where you find u and then you find du by taking the derivative. And you label one of your given functions dv, and to find capital V or capital V, to find v as in violin, you just take the integral of what you let dv equal to. So the u part is the same, no change there, but dv to v is actually integration. Now I found this handy PDF off the internet. This is from Berkeley University, I think, from their Academic Support Center. And they offer some guidelines for selecting u and dv. It says here, choose u to be the function that comes first in this list. So if you have a logarithmic function, then or natural log, then let that be your u. If you have an exponential function, then chances are you're going to let that be your dv and integrate it. Let me caution you, with integration by parts, you may have to do like with the L'Hopital's rule, you may have to use the integration by parts more than once. So let's start with a basic example. And let me share my screen. There we are. We need to integrate x cubed times natural log of x dx. Now I'm just going to use the advice given on this Berkeley PDF sheet. A logarithmic function comes before an algebraic function, so we'll let our logarithmic or natural log of x be our u. All right, so we'll let natural log of x be our u. And when we take the derivative of both sides, du is just 1 over x dx. Now we need to label dv. So we'll let dv equal to x cubed dx. Now to find v, you just integrate x cubed. So when we integrate x cubed, we get x to the fourth power all over 4. Now let's plug everything into our integration by parts formula. U is natural log of x times v, which is x to the fourth power over 4, minus the integral of v. V is x to the fourth over 4, times du, and du is 1 over x dx. Now, a few things before we deal with the integral part. Let's move the 1/4 x to the fourth to the front of our natural log of x. Right here, we can simplify the x's, making that x to the third. Bring out that 1/4, that's negative 1/4. Integral of x cubed dx. Oh, and that looks like a y. Sorry about that. Let me fix that. Now we're ready to integrate. So we got 1 over 4 x to the fourth times natural log of x minus 1/4 times x to the fourth power over 4. Now, because this is an indefinite integral, we need a plus c to denote any possible constant. So our final answer is 1/4 times x to the fourth natural log of x minus 1/16 x to the fourth plus c. And let me check my answer. Yep, our answer is correct. Let's look at our next problem. I'm going to leave our parts formula up here. Hang on just a minute. All right, let me copy the next problem. Sine x, the integral of sine x times natural log of cosine x dx. Let's look at our handy chart courtesy of Berkeley. L comes before t, or trig function. So that means we'll let u equal to our natural log cosine x. So the derivative, remember the derivative of natural log is 1 over your given function, in this case 1 over cosine, times the derivative of your function, or derivative of cosine, The derivative of cosine is negative sine x. So we have negative sine x over cosine x dx. It's tempting to change this to negative tangent, but hold off on that. We may not even need to do that. Now we got to find or label our dv. Dv is sine x dx. Now to find v, we integrate both sides. The integral of dv is just like taking the integral of dx. That would just be your letter, in this case v. And the integral of sine x is negative cosine x. All right, let's plug everything into our parts formula. U times v. So that would be natural log cosine x times negative cosine x minus the integral of v, or negative cosine x, times du, which is negative sine x over cosine x dx. Now, a few things we can do before integrating. This negative cosine x, move it to the front of your natural log. Next up, the cosines cancel. And all of our negative signs, when we multiply them together, give us a negative sign. So all that's left to integrate is sine x dx. The integral of sine x dx is negative cosine x again. And I'm just bringing everything else down. And let me see how Berkeley wrote their final answer. Hang on just a minute. Okay, cool. When we change our double negatives here to a positive sign, we get our final answer. Negative cosine x, natural log of cosine x, plus cosine x, and don't forget your plus c. All right, let's look at our next problem. Integrate the inverse sine of x dx. Now I'm going to copy most of this so I will not mess up the integral formula for inverse sine. And I thought the same thing too. I'm reading the notes here, saying at first it appears that integration parts by parts does not apply. You can always let dv equal to your dx. There's no rule that says you can't do that. So when you integrate both sides, you get v is equal to just plain x. So that's allowed. Now let me walk you through what they did here for the other part. They let u equal to the inverse sine x. And the derivative of inverse sine is a formula unto itself. It is 1 over the square root of 1 minus x squared times dx. Now let's plug everything into our integration by parts formula. We have u, which is inverse sine x, times v, which is x, and I'm going to go ahead and move that to the front, minus the integral of v, which is x, times du, which is the 1 over square root of 1 minus x squared dx. We're done with this part, so I'm going to erase it because we need to evaluate, to do the integral, we need just a regular u substitution. So here I'm going to let just u equal to 1 minus x squared. So du is equal to negative 2x dx. Now what we're actually trying to plug in is x dx, but we got this negative 2 attached to it. No problem, we'll just divide both sides of our derivative by negative 2. And that gives us negative 1/2 du equal to x dx. Well, now we're ready to plug that into our integral. In place of x 1 dx, that's our negative 1/2 du. But I'm going to move the negative 1/2 in front because it's a constant. And we got du. And what goes under the radical is just plain u, but it's square root of u. Square root of u, as y'all know, is the same thing as u to the 1/2 power. And in order to integrate du over u to the 1/2 power, we need to rewrite it as a negative exponent. Now we're ready to take the antiderivative or undo the power rule for derivatives by adding 1 to the original exponent. And that is actually what we divide by our new exponent. So that gives us u to the 1/2 power over 1/2. When we flip the fraction or divide by 1/2, we get 2u to the 1/2 power. All right, so let's bring that over. We have our x inverse sine of x plus 1/2 already on the outside times our 2u to the 1/2. And of course, the 2's cancel. Now, the last thing we need to do is back substitute what u was originally. Now, u was originally 1 minus x squared. So that would become square root of 1 minus x squared when we change the 1/2 back to a radical. And again, don't forget your plus c. Let me check it. And our answer is correct. Let's look at another problem where you have to use integration by parts. And let's try this one. Yeah, this one's a little challenging. I already tell you, or you already just saw it. That we have to use integration by parts several times. So let me wipe our dry erase paintboard. And let's see. Going back to this handy mnemonic device that this website shared, an algebraic function is slightly over a trig function. So we'll let the algebraic function be our u. So we'll let u equal to x squared. And du equal to 2x dx. And we'll let dv be our sine of x dx. And to get v, you integrate both sides. So v is equal to negative cosine x. All right, let's plug everything into our parts formula. U times v, or x squared, times our negative cosine x. And I'll go ahead and move the negative sign in front. Minus the integral of v, with v being negative cosine x, times du, which is 2x dx. And let's clean that up a bit. Our negative time negative changes to a positive sign. And let's move the 2 in front. Okay, we still can't integrate. We have x times cosine x. So let's use integration by parts again. So second go around, we'll let u equal to x. And when we take the derivative of both sides, we got du equal to dx. The next thing we need to label is our dv. And we'll let that be cosine x dx. And to find v, again, you integrate both sides. So v is equal to sine x. Now be careful. Right here, we're using our parts formula again. So whatever's in front, you bring down. Negative x squared cosine x plus 2. Now let's use our parts formula again. U is x, v is sine x, minus the integral of v, which is sine x, and du is just plain dx. Well, now we can find the integral. We know that one. The integral of sine x is negative cosine x. And with this negative sign already outside, a negative times a negative, that will become a positive cosine x now. And the last thing we need to do is distribute that 2. So our final answer is negative x squared cosine x plus 2x sine x plus 2 cosine x plus c. Let me go back to our notes and see if our answer is correct. 2 cosine. Negative x squared is 2x plus 2 cosine x. Yep, everything is correct. So you may have to use the integration by parts formula more than once. Let's look at another problem. And hang on just a minute. Let me copy and paste this one. Okay, according to our, go back home here. Algebraic function is way over exponential function, or e for short. So that means we'll let our u be 7x. Okay. So taking the derivative of both sides gives you du equal to 7dx. That leaves dv to be equal to e to the 6x power dx. Now, I'm not going to show it to you here, but You can actually look this up, or you can perform like a use substitution to get what V is. V is actually equal to 1 over 6 e to the 6x power. Basically, whatever your exponent is, whatever the number is, it's usually the reciprocal in front. Now let's plug everything into our parts formula. U is 7x times V, which is 1 over 6 e to the 6x power. Let's go ahead and simplify and multiply. We have 7 over 6 x e to the 6x power minus the integral of v, or 1/6 e to the 6x power, times du, which is 7 dx. And let's move that 7 and 1/6 outside, making it 7 over 6 times the integral of e to the 6x power dx. Now, I did say I wasn't going to show you, how to go from how to integrate e to the 6x power, but I need to show you anyway. We're not using the parts formula again. We're just doing a regular use substitution by letting u equal to 6x. So du is equal to 6 dx. And this is how you get the 1 over 6 part. You just simply divide both sides of your derivative by 6. So 1 over 6 du is our dx. So we already know from earlier that this integral is actually 1 over 6 e to the 6x power. And we'll just simplify a little bit. Our final answer is 7 over 6 x e to the 6x power minus 7 over 36 e to the 6x power plus c. Let's look at another problem that involves a trig function. So give me 1 second here. All right, let's try this one. Okay, I need to go back to my handy mnemonic chart here. Trig function is slightly over exponential function. So we'll let the trig function be our u. So here we go. We'll let u equal to sine of 10 theta. So du is equal to cosine of 10 theta times the derivative of 10 theta. And the derivative of 10 theta is just 10. So our final du is 10 cosine 10 theta d theta. Now the dv part is the rest of our problem. 10 e to the 10 theta d theta. Using what we learned from the last problem, e to the 10 theta d theta, its integral actually, I can leave that 10 out for right now. Integral of e to the 10 theta d theta is 1 over 10 e to the 10 theta. So that is our v. And I'm going to do something I haven't done with the other problems, and that is plug in our UDV. And our UDV, tell you what, let me let u equal to 10 sine of 10 theta. So that would give us actually 100 cosine of 10 theta. So I'm going to plug in actually just our original problem. And we'll plug in the rest of the integration problem. U is 10 sine of 10 theta times V, which is 1/10 e to the 10 theta minus V, which is 1 over 10 e to the 10 theta and then let's see what's left times du, which was 100 cosine of 10 theta d theta. Now, a few things we can do before we integrate by parts again. Up here, the tens cancel. And right here, 10 can go into 100 10 times. So let me erase our u and du and dv parts. Now let's write down what we currently have. We have the integral of 10 e to the 10 theta sine of 10 theta d theta equal to e to the 10 theta sine 10 theta, minus the integral of 10 e to the 10 theta cosine 10 theta d theta. And it looks like we have to use integration by parts once again. So let me see if I can erase this part since we're done with it now. And then try and move this up here. Okay, there we go. Now, on to round 2. Still going to let u be our trig function and dv be our e function. All right, here we go. U equal to cosine of 10 theta d theta. Oh, no, we don't need the d theta part, sorry. So the derivative, or du, is negative sine 10 theta d theta, and this is the chain rule that we're using, times the derivative of 10 theta. So that gives us, I'm just moving it over here, du is equal to, well, the derivative of 10 theta is just 10. And moving it to the front gives us negative 10 sine of 10 theta d theta. Now your dv is equal to, and here honestly it doesn't matter. You can have that 10 with your u cosine 10 theta, or you can have it with the integral. It does not matter. So we'll let dv equal to 10 times e to the 10 theta d theta. Actually, I do need to move that 10 right here. Sorry about that. So that's actually going to turn this into negative 100 in front. Now to find v, we integrate both sides. And v is equal to 1 over 10 e to the 10 theta d theta. All right, we're ready to use integration by parts again. Bring down what's in front, the E10 theta times sine of 10 theta minus, now this is the part where we use our integration by parts formula again. All right, so U was 10 cosine of 10 theta times V, which is 1/10 e to the 10 theta don't need the d theta up there anymore, minus the integral of v du. V is 1 over 10 e to the 10 theta times du, which was negative 100 over here, negative 100 sine of 10 theta d theta. Now let's clean this part up just a bit. Right here, the 10s cancel. And right here, 10 can go into 100 10 times. So let me bring down carefully what we currently have. E to the 10 theta sine of 10 theta distributing this negative sign carefully, we got negative e to the 10 theta cosine 10 theta and then a negative times another negative gives us a negative sign, minus the integral of, hold on just a minute, minus the integral of 10, moving the 10 in front, that's in blue, e to the 10 theta times sine of 10 theta d theta. And it looks like we're going round and round in circles because this is the exact same thing that we started out with kind of earlier. So there's no end in sight to this problem, or so it seems. I'm going to show you a way to solve this problem. Let me make some room here. Okay, this last step is our current step, so I can erase the rest of it. We've already simplified, multiplied everything we need to do. Okay, let me just bring this up here. Alrighty. Let me bring this up here and shrink it a little bit. Let's see, let me shrink this part too. Okay, and I think I cut off part of it. I'm so sorry. That should be an E right there. Now, it looks like there's no end in sight to this problem. But if you compare the left side to the right-hand side, part of the right-hand side, we have an integral of 10e to the 10 theta sine 10 theta d theta on the left side. And we have the same thing over here. Those are actually like terms that you can combine together. Just like if this were x and this were negative x, then you can move the negative x to the left-hand side by adding all of this that I've underlined over on the right-hand side, by adding that to both sides. Okay, so I'm going to do the same thing here. Let me erase this line. I'm going to add the integral of 10e to the 10 theta, etc., to the left-hand side. Now on the right-hand side, these like terms cancel out. And on the left-hand side, since we got two of them, that's like saying x plus x is 2x. So two of these same integrals is actually 2 integral of 10e to the 10 theta sine of 10 theta d theta equal to what's remaining on the right-hand side. Now, what we were trying to solve for was this actual problem. But we got that 2 in front of the integral. So the very last step is divide both sides by 2. On the left-hand side, the 2's cancel, and you got the original problem that you're trying to solve. And the right-hand side, the only thing you need to do is add a plus c to your answer. So watch out for problems like this one that seem to go forever. If that happens, just kind of follow the steps I did here. This concludes lesson 16 on integration by parts. Either later today or first thing tomorrow, I will share this video in Blackboard announcements. And if I can find another video on parts that I did, I'll share that one as well.